Those who have joined the class can give their attendance in the chat box. I repeat, those who have joined the class may give their attendance in the chat box. So it is around 11:34 a.m. I can see that 7 people have joined. So we will not waste time. Just give me a minute so that I can present my screen. Can anyone respond whether my slides are visible or not?
Yes, sir, they are visible.
Okay, thank you. Okay, good morning to all of you. So, in continuation of the last class, if you remember, in the last class, we started the topic called determination of stiffness matrix by direct stiffness method. If you remember, in the last class, we have taken one element. For this one single element, how to get the stiffness matrix by direct stiffness method that we have seen. In today's class, what we will do, we will take a little bit complicated problem. In that complicated problem, there will be more than one number of elements. Then how, by this direct stiffness matrix method, how we can determine the global stiffness matrix for the entire problem consisting of more than one element. That is the main target in this class. So let us solve a problem. If you remember, we have solved this problem by potential energy approach also in some previous classes. If you see some 2 or 3 previous classes back, we have did this problem. That means we have found out the global stiffness matrix for the entire problem by potential energy method. But today we will solve the same problem by direct stiffness method, and then we will understand that what is the difference between the use of direct stiffness method and the potential energy method. Okay, so let us read the problem. Problem tells you that derive the global stiffness matrix. Wait, somebody is joining. Okay, so derive the global stiffness matrix, displacement and nodal force vector for the three carts interconnected by a system of linear elastic springs shown in the figure by direct stiffness method. That means what I need to find out? I need to find out the global stiffness matrix. And by global stiffness matrix, I mean the overall stiffness matrix for the entire element that I need to find out, as well as I need to find out the displacement vector in matrix form and nodal force vector present in this entire problem in matrix form by direct stiffness method. So we know that in direct stiffness method, the very first step is what? The very first step is writing down the governing algebraic equation for the entire problem. If you see, in the entire problem comprises of spring elements. The entire problem comprises of spring element, and we know that the governing differential equation for a spring element is given by nothing but the restoring force, that is F is equal to minus K into X, where K is the stiffness of the spring element and X is the deflection of the spring element. Fine. So this will be my governing algebraic equation in order to solve this problem by direct stiffness method. And while solving the problem, we will not take this minus sign into account. Okay, so I can say that the governing algebraic equation of this problem is F is equal to K into delta, where K is the stiffness of each and every element. For this is my element number 1, stiffness present is stiffness of the element is K1. Element number 2, stiffness is K2. Element number 3, stiffness is K3. Element number 4, stiffness is K4. Element number 5, stiffness is K5. And what is delta? Delta is the displacement or the deflection of the spring. Since 5 elements are present, so there will be 5 different displacements for each individual element. So let for element number 1 displacement is delta 1. For element number 2 displacement is delta 2. For element number 3 displacement is delta 3. For element number 4 displacement is delta 4, and for element number 5 displacement is delta 5. Is it clear so far? Any doubt? Hello.
No, sir.
Okay. Wait. Fine. So we have the governing differential equation as F is equal to K into delta. And if you see here, delta will be in terms of U, because displacement of each and every node is in terms of U. So I can write F is equal to K into that displacement delta as U. In matrix form, the given algebraic equation is written as force vector F is equal to matrix, that is global stiffness matrix K into displacement vector U. What is this K? This K is my global stiffness matrix that I need to determine for the entire problem. What is this F? This F is nodal force vector that also I need to determine. And what is U? U is the nodal displacement of the entire problem that I need to determine. So if you see in this particular problem, there are total 5 elements are there. 1, 2, 3, 4, and 5. So there will be 5 different algebraic equation for each individual element. There will be 5 individual stiffness matrix for each element, and those individual stiffness matrix for each element is known as local stiffness matrix. Local stiffness matrix. That means this governing algebraic equation is valid for this element also, that for this element, for this element, for this element, as well as for this element. There, that means there will be total 5 different algebraic equations satisfying the given conditions of the problem. So if there are 5 different equations, definitely there will be 5 different this stiffness matrix for each and every element, and those individual stiffness matrix for each and every element is known as local stiffness matrix. Is it clear to all of you? Any doubt so far?
No, sir. No, sir.
Okay, now let us identify how many nodes are present in the problem. I can see this is node number 1, this is node number 2, this is node number 3, and this one is node number 4. But since the node number 4 is fixed, so displacement of this node will be 0. So I will not consider it as a node. So I can see that in the entire problem, total 3 nodes are present. Element number 1 is connected between node number 1 and the fixed end. Element 2 is connected between node 1 and node 2. Element 3 is connected between node 1 and node 3. Element 4 is connected between node 2 and node 3. Element 5 is connected between node 2 and node 3. So since there are 3 nodes present in this problem, and if you remember, I have told you in the last class that in this direct stiffness method, first of all you have to identify how many nodes are present in the entire problem, because number of nodes decides the order of the stiffness matrix. Since 3 nodes are present in this particular problem, so the order of global stiffness matrix will be 3 cross 3. Is it clear to all of you? Any
Yes,
doubt
sir.
so far? Any doubt so far?
No, sir.
Okay, so that means, so now we came to know that this entire problem, at last the global stiffness matrix which I will get, that will be a 3 cross 3 matrix. Why? Because 3 nodes are present in this entire problem. If any problem 4 nodes are present, then the global stiffness matrix will be a 4 cross 4 matrix. If any problem say 8 nodes are present, then the global stiffness matrix will be an 8 cross 8 matrix, and so on. Okay. So my first task is to write individually for each and every element. Let us write the given algebraic equation in matrix form. So let us consider first element number 1. Now this is my element number 1. It is connected between the first node and the fixed node, and this is your node number 1. Node number 1 is subjected to nodal force F1 and displacement U1, and I know that the governing differential equation for this particular element is what? It is F is equal to K into delta. So for first element, since this is element number 1, since this is element number 1, so I can write equation number 1 as F1 of 1. F1 of 1 means force acting at node 1 for the first element. F1 represent force acting at first nodal point on the first element. F1 of 1 is equal to, this K will become K1 into this delta will become delta 1 for the first element, and I can see that at this particular end displacement is 0, so the delta 1 will be equal to nothing but u1 in this direction. So I can write this equation as f1 of 1 is equal to k1 into u1. In matrix form, I can write this equation as matrix K1 into matrix U1 into matrix F1 of 1. And what will be the order of the stiffness matrix? Order of the stiffness matrix will be equal to the number of node present in this first element. Since in the first element only one node is present, this is node number 1, definitely this node is also present, but in this node there is no deflection, so that's why I will not consider it as a node. So only one node is present, so the stiffness matrix which I will get for element number 1 will be of the order 1 cross 1. That means only one one row, one column, one element, that is K1. So equation number 2 becomes matrix K1 into displacement vector U1 equal to force vector F1 of 1, and this F1 of 1 represent force acting at nodal point 1 on the first element. This is my equation number 2, that is the governing algebraic equation number 2 in matrix form for the first element. Is it clear to all of you? Any doubts till equation number 2? Hello.
No, sir.
Okay. Similarly, I have to generate this type of equation. Which type of equation? Similarly, I have to generate this type of equation for the remaining elements. So let us generate it. So for second element, if I see second element, this is my second element. It is connected between node number 1 and node number 2, and both the nodes are subjected to nodal forces as well as nodal displacement. So let us draw the element first. This is your second element. Yes. So this is my second element connected between node 1 and node 2. Node 2 is subjected to nodal force F2 and displacement U2, and node 1 is subjected to nodal force F1 and displacement U1. I know that the governing algebraic equation for this element is also F is equal to K into delta, but this time this governing algebraic equation will have two forms. Two times you have to write, one for this particular node, another one for this particular node. So two equations you will get for this single element. In the last element, since the fixed end was 0, so I only got one equation. So let us write the equation. Fine. So if I assume that the entire system is moving along this direction, and if I assume that F2 is greater than F1 and U2 is greater than U1, that means the entire system is moving in positive x direction, then in that case if I want to write my governing algebraic equation at node 2 for element number 2, how I can write? That is force acting at second node is F2, but this time this F2 is acting on element number 2, so this is F2 of 2 is equal to K becomes K2 into delta becomes delta 2 for second element. Similarly, at the first nodal point, the governing algebraic equation becomes F1, but this F1 is acting in the second element, so F1 of 2. So F1 of 2 is equal to K2 into delta 2. Again, I can write these two equations as F2 of 2 is equal to K2 into delta 2 is what? If I assume that forces and displacement at node 2 is greater than node 1, then this displacement delta 2 will be how much? U2 minus U1. So I can write F2 of 2 is equal to K2 into, in place of delta 2, I can write U2 minus U1. And you know that if you write the equilibrium equation for this element, this is plus F1 plus F2 equal to 0, or you can write F2 is equal to minus times of F1. So before that, let us substitute F1. So I can write F1 of second element is equal to K2 into delta 2. Now in this case, delta 2 will be U1 minus U2 because F2 is minus times of F1. So K2 becomes U1 minus U2. Now again, if I rearrange this particular equation and this particular equation, it will take the shape as F1 of 2, that means force acting at node 1 but on second element, is equal to K2U1 minus K2U2. Similarly, F2 of 2 is equal to minus K2U1 plus K2U2, that is this expression, that is this two expression. Now I have to write these two equation in matrix form. How I can write in matrix form? That is stiffness matrix K into displacement vector matrix U equal to nodal force vector matrix F. Fine, but I have to decide what will be the order of my stiffness matrix. Now order of the stiffness matrix is decided by how many number of node present in the element. If I see in this element only two nodes are present, that is node 1 and node 2, so the order of the stiffness matrix will be a 2 cross 2 matrix, that means 2 rows and 2 column. And I also know that this line I have written here 1 2 1 2, this one means for the first node, values for the first node. This second row of means the values for the second node. And similarly, if I talk in terms of column, these particular values is for first node and these particular values is for second node into displacement vector. For at node number 1, displacement vector is u1, u1. At node number 2, displacement vector is u2, u2. Equal to, this is force vector. At node 1, force vector is F1 of 2, right? F1 of 2. At second node, the nodal force vector is F2 of 2, right? F2 of 2. Now only one thing is left, that is the stiffness matrix, and that stiffness matrix will be, so this is what, this value is coefficient of u1, this value is coefficient of u2 from the first equation, this value is coefficient of u1 and this value is coefficient of u2 from the second equation. So I can write k2 minus k2 minus k2 minus k2 minus k2 k2 k2. So the final equation becomes k2 minus k2 minus k2 k2 into matrix u1 u2 column matrix u1 u2 equal to column matrix nodal force vector f1 of 2 f2 of 2, that is equation number 3. Is it clear to all of you, equation number 3?
Yes, sir.
Fine. Any doubt? Other people please respond whether any doubt is there or not.
No, sir. No, sir.
Okay, so this matrix, which matrix? This particular matrix. This is a stiffness matrix which is valid for only element number 2. This matrix is known as your local stiffness matrix. That means in this problem there are total 5 elements are there, so there will be total 5 different local stiffness matrix, but there will be only one global stiffness matrix for the entire problem. Okay, so this is the matrix equation for element number 2. So now similarly let us find out the matrix equation for the third element. I can see that the third element is connected between nodal point 1 and nodal point 3, and both node 1 and node 3 are subjected to nodal force vector and nodal displacement vector. So first of all, let us draw the element first. So this is your third element connected between node 1 and node 3, subjected to nodal forces F1 U1 at node 1 and F3 U3 at node 3. Then the governing algebraic equation. Again, there will be two governing algebraic equation, one for node 1 and second for node 3. So let us write it down. What will be the governing algebraic equation? If I talk about node 1, it will be say yeah, sorry. And if I assume that the entire element, again if it is moving in this direction, that means I can assume that the values at node 3 is more than that at node 1. That means I can assume that f3 is greater than f1. Then in that case, if I want to write down the algebraic equation at node point 3, how I will write? F3, that is force acting at node 3 but on element 3. So F3 of 3. F3 of 3 is equal to how much? It is equal to K3 into delta 3. But since this node is greater, nodal values at this node is greater than this node, so this delta 3 will be how much? U3 minus U2. So F3 of 3 is equal to K3, sorry, U3 minus U1. So F3 is equal to K3, U3 minus U1. Similarly, for nodal point 1, I can write F1, that is nodal force acting at node 1 but on element 3. So F1 of 3 is equal to K3 into again delta 3. Since U3 is greater than U1 and by equilibrium conditions I know that F1 plus F3 equal to 0 or F3 equal to minus times of F1. So this delta 3, if in F3 of 3 delta 3 is U3 minus U1, then in F1 of 3 it will be U1 minus U3, that is U1 minus U3. Again if we rearrange, if we rearrange this equation and this equation, I can write F1 of 3 is equal to K3U1 minus K3U3, and this equation has F3 of 3 is equal to minus K3U1 plus K3U3. Fine. Again, I can see that this third element is connected between two nodes. So there will be two algebraic equation, one for node 1, another one for node 3. Now I have to write these algebraic equation in terms of matrix form. Before that, we have to decide that what will be the order of the stiffness matrix. I know from the diagram that in the third element only two nodes are present, that is node 1 and node 3. So the order of the stiffness matrix will be a 2 cross 2 matrix. And so this is your K matrix into displacement field vector matrix into the nodal force vector matrix. Since this element is connected between node 1 and node 3, so this will be the first node, this will be the third node. Similarly, this will be the first node, this will be the third node. And inside the stiffness matrix, this is nothing but the coefficient of u1 in the first equation. This is coefficient of u3 in the first equation. This is coefficient of u1 from the second equation. This is coefficient of u3 from the second equation. Fine. So I can write that K3 minus K3 minus K3 K3 into at node 1 displacement is u1, so u1. At node 3 displacement is u3, so u3 equal to nodal force vector. At node 1 nodal force vector is f1, but it is applied on third element, so f1 of 3. At the third node nodal force vector is f3, you can see it is f3, but it is applied on third element, so it will be f3 of 3, which is equation number 4. Is it clear to all of you? Equation number 4 for third element. Any doubt so far?
So clear, sir.
Okay. Other people please respond whether it is clear or not.
Clear, sir.
Okay. Similarly, I have to do the same procedure for fourth element as well as for fifth element. So for fourth element, if I can see from the diagram, the fourth element is connected between second node and third node. And both the nodes are subjected to nodal force as well as nodal displacement. That means again there will be two governing algebraic equation, one for node 2, another one for node 3. And since element 4 is connected between two nodes, so I know that the order of the stiffness matrix will be a 2 cross 2 matrix, in which the first row will be the second node, Third row will be the third node. First column will be the second node. Second column will be the third node. So let us find out for the fourth element. This is that fourth element. Fine. So I can write the governing differential equation as, again, if I assume that F3 and U3 is greater than F2 and U2, then the entire system is moving along this particular direction. That is along positive x direction. So I can write for a third node as F3 acting on third node, but it is also acting on fourth element. So F3 of 4 is equal to K4 into delta 4. This delta 4 will be U3 minus U2. Similarly, for node 2, the governing algebraic equation will be F2, that is F2 acting, this force acting on node 2, but it is acting on element number 4. So F2 of 4, see, F2 of 4 is equal to K4 into delta 4. So from the diagram it is very much clear that F2 plus F3 equal to 0. So F3 equal to minus times of F2. So this delta 4 becomes U2 minus U3. U2 minus U3. Again you rearrange it. If you rearrange this expression, if you rearrange this expression and this expression, for this expression you will get this value, for this expression you will get this value. That means what we are doing, we are just opening the bracket. Then the governing algebraic equation in matrix form, it is written as stiffness matrix into displacement field vector matrix equal to force vector matrix. Order of the stiffness matrix will be 2 cross 2 because there are two nodes present, and we also know that this is node number 1, this is node number 2. Again, this column matrix is node number 1 and this column matrix is node number 2. And this is what? This is the coefficient of U2, since it is in U2. This is what? Coefficient of U3. Again, this is coefficient of U2 and this is coefficient of U3. So let us write it down. So from the first expression along the second node, this is K4, K4. For the second expression, for second expression, that is for this expression, coefficient of U2 is minus K4. Again for first expression, coefficient of F2 is minus K4, and for second expression again coefficient of F4, K4, sorry, U3 is K4. So I can write K4 minus K4 minus K4 K4 into column matrix U1 U2 U1 U3 equal to nodal force vector matrix F2 of 4 and F3 of 4. Is it clear to all of you? Equation number 5. Any doubt so far?
Yes, sir.
Okay. Other people, please respond whether any doubt is there or not.
No, sir. No, sir.
Okay. Similarly, the last element, for the last element, that is element number 5, which is connected between node 2 and node 3, having displacement and nodal force vector as U3 F3 and U2 F2. Now let us find out the algebraic equation by direct stiffness matrix method for element number 5. So first of all, let us draw the fifth element. This is the fifth element which is placed between node 2 and node 3. And if I assume that forces and displacement at node 3 is greater than node 1, then F3 comma U3 is less than F2 comma U2. Fine. So the governing differential equation becomes, governing algebraic equation becomes F is equal to K into delta. So if I talk about nodal point 3, how I can write? I can write it as F3, but acting on fifth element is equal to K5 into delta 5, and since this node is having greater value as compared to this node, so delta 5 will be u3 minus u2. See, if 3 of 5 is equal to yes, if 3 of 5 is equal to k5, u3 minus u2. Similarly, for the second element, if I want to write down the algebraic equation, it will be f2. It will be F2 because it is acting at nodal point 2. On which element it is acting? On element number 5. So F2 of 5 is equal to stiffness, that is K5, and deflection. In this case, deflection will be U2 minus U3. Why U2 minus U3? Because if you draw the FBD of this particular arrangement, it will be F1 along positive x-axis, F3 along positive x-axis. So F3 will be minus times of F2. Done. So next what we will do, we will substitute, that is we will multiply this expression with this one and the same expression with this one. So I can write this particular equation as K5U2 minus K5U3. Similarly, this particular expression as minus K5U2 plus K5U3. And I know that this element is connected between node 3 and 2 and 3. So this will be your node 2. This is your node 2. This is your node 3. Is it clear to all of you? Any doubts so far?
No, sir.
Okay, that means from the first equation, this is coefficient of u2 and this is coefficient of u3. From the second equation, that is this is coefficient of coefficient of third u3, and this is also coefficient, this is coefficient of u3 into column matrix. At second node displacement present is u2, at third node displacement present is u3, which is equal to the nodal force vector. Nodal force vector will be f2 acting on element 2 button, that is f2 of 5, that is f2 means force acting at nodal point 2 on fifth element. Similarly, this will be this particular value, that is f3 acting on the fifth f3, that is acting on element number 5. So I get this particular equation number 6. Is it clear to all of you? Equation number 6. Same process I am following, only I am changing the element and the boundary conditions are changing. Is it correct?
Yes, sir. Yes, sir.
Fine. Similar. So if you see, we have framed the algebraic equation in local matrix form, starting from equation number 2, equation number 3, equation number 4, and equation number 6. So next step is what? Next step is I need to assemble. I need to assemble the overall matrix equation for all the individual matrix equation which we have just now calculated. So how to assemble it? In place of positive, put the positive sign. In place of negative, put the negative sign, and then try to assemble. How I will assemble? Now, since you know that the entire problem consists of three elements, so the global stiffness matrix for this problem will be also three nodes. Will be also three nodes, and the order of the stiffness matrix will be 3 cross 3 order. So how we will assemble it? Very simple. This is first row and first column. Identify which value has first row and first column. Let me see. From equation number 2, first row, first column is K1. For second element, no, there is no other. Yes. I need to find out what? I need to find out this 1 1. So let us identify where is 1 1. 1 1 K1, 1 1 K2. So K1 plus K2. Then for third element 1 1, that is K3. No, after that it is not there. So this coefficient becomes K1 plus K2 plus K3. Is it clear to all of you? First row, first column. Is it clear?
Yes, sir.
Other people, please respond. This is
Yes, sir.
first row and first column. Any doubt so far?
No, sir. No, sir.
No, sir. No, sir. No,
Okay.
sir.
Similarly, next I need to evaluate the first row and the second column, that means this value. So again I have to check from the equations of algebraic equations of each and every element which one is having this first row and second column value. So let us check. I will not use equation number 2 because there is no first row and second column. Equation number 3, yes, it is present. First row, second column, value is minus K2. So you can write over here minus K2. Similarly, first row, third column. So first row, third column. Let us find out. No, I will not use equation number 2 because there is one row and one column. Then first row, second column. We cannot use. Next is first row, third column. Yes, we can use first row and third column. The value is minus K3. Then see, minus K3. First row and third column. Likewise, you have to evaluate the entire matrix. Is it clear to all of you? Hello?
Sir.
Fine. That means what you need to do, simply identify, say for second row, if you want to write down the stiffness matrix, that means from all those equations which we have derived just now, just find out what is second row and first column. This coefficient value you will get. Similarly, for this coefficient value, how you will get? Second row, second column. If you analyze, you will get this particular value, that is K2 plus K4 plus K5 and so on. And so on. So this is, that is this particular matrix is known as your global stiffness matrix. This particular matrix is known as your global stiffness matrix into nodal displacement vector. Since three nodes are present and all the three nodes are displaced, so the nodal displacement vector will be u1 u2 u3, which is equal to nodal force vector, that is along the first node force acting is F1, for along the second node force acting is F2, and along the third node force acting is F3. And in this expression, what is F1? F1 is a part of first element, it is a part of second element, it is a part of third element. All these three, if you combine, you will get this F1. Similarly, what is F2? F2 is what? F2 again, it is a part of some element, that is F2 of 2 acting on the second element, acting on the fourth element, acting on the fifth element, and so on. If you do it, you will get this type of matrix. That is, you will get this particular expression. And this is your final answer. That means in this expression, this part is your global stiffness matrix. This part is your displacement field. And this portion is the total force acting on the element. Is it clear to all of you? Any doubts so far?
No, sir.
Okay, so this is the final answer of this problem. So I hope that in this class you might have understood. I hope that in this class you might have understood how to generate or to derive the global stiffness matrix when in a single problem more than one element is there. Okay, so with this, I end my today's lecture over here. From the next lecture, that is, it is scheduled on Monday. From the next lecture onwards, we will move on to the next sub part or subtopic of this subject. Okay, so if anyone is still left to give his or her attendance, you can give the attendance, or else you can leave the meeting. Thank you.